So now that we've learned a little bit about oxidation reduction chemistry, we're going to apply what we've learned to something called an electrochemical cell. So an electrochemical cell or a voltaic cell, these two words mean the same thing. It is essentially an apparatus that allows a redox reaction to occur by transferring electrons through an external connector. So this is what an electrochemical cell is going to look like in your Regents questions. Eventually you need to learn what all these parts are, what their names are, what happens there, and how this overall apparatus works. But like I said, basically it's going to allow a chemical reaction to produce a spontaneous electric current by converting chemical energy to electrical energy, which is essentially what a battery is. So an electrochemical cell is a battery. Now this doesn't look like the modern day batteries, but the same principles that we're learning in these electrochemical cells can be applied to how batteries that you use actually work. So let's start talking about some of the parts. So in this electrochemical cell, we have two containers, which we call half cells, and there are metal bars that are placed into these containers. I have a silver one on the left and a goldish color one on the right. These bars are called electrodes, and there's two different types, and they have two different names. The first one is a cathode. This is an electrode where reduction occurs. So in our example, our cathode is on the right-hand side, the gold-colored bar, and like I said, this is where reduction occurs. In an electrochemical or voltaic cell, the cathode is the positive electrode. So we're going to label our little bar here with a positive sign to show that. So one way you can remember that the cathode is positive is if you look at the letter T in cathode, okay, not so much in this font, but the letter T is kind of like a positive sign. So that always reminds me that the cathode is positive. So once I know what the cathode is, I can label it positive, and that can help in answering questions later. So one way to remember that reduction happens at the cathode is if we take away some of these letters here, I can reduce this down to red cat. So think of a red cat, and you remember that reduction happens at the cathode. Next we have the anode. That's our silver bar. This is the electrode where oxidation occurs. So the anode is where oxidation occurs, and it is the negative electrode. So the way I remember that is in the letter A for anode, it has this little line that kind of you draw when you're making a capital A, and it's like a negative sign. So that's how I remember to label my anode negative. And to remember that oxidation happens here, just like in the red cat example, we'll just take away some of these letters and we get an ox. So think of an ox. Some people even sell t-shirts that have red cats riding on the back of oxes. It's a little bit of a chemistry joke. So if you remember red cat and ox, you remember reduction happens at the cathode and oxidation happens at the anode. So how do you know which electrode is which? So one of the things you're often asked to do is label an electrochemical cell, and if you mess this part up, you're going to get everything backwards. So you really need to know which electrode is which. There's a really easy way to determine this, and that's to use table J. So table J we've seen before. This is our activity series of metals. Electrodes are always metals, so we're just looking at the left-hand side of our chart here. And the anode is always going to be the more active metal according to table J, which means it's going to be the one highest on the list. So as soon as you get an electrochemical cell, you look at your two metals that your electrodes are made out of, you go to table J, and the highest one is your anode that you label negative, and you write oxidation happens there. Okay, so next we're going to draw and label an electrochemical cell. So like you saw in the previous picture, there are containers, which we call half cells. And this half cell on the left, sometimes we'll label this half cell 1, or if it's has a specific electrode in it, we'll name the half cell based on the electrode that's in it. And there's a liquidy environment, there's a aqueous salt solution in these half cells. So this half cell happens to have zinc chloride in it. On our half cell on the right, we also have a salt solution. This one will have copper chloride, copper 2 chloride. So these are aqueous solutions of salts. So of course these ions will dissociate in water. The zinc chloride is going to dissociate into zinc ions and chloride ions. And the copper 2 chloride is going to dissociate into copper 2 ions and chloride ions. So really we just have water with these ions floating around in these separate half cells. Next, I'm going to put the electrodes in. So on the half cell on the left, I have a zinc electrode. In the half cell on the right, I have a copper electrode. Next, we're going to attach a wire to these. Still, nothing is happening yet. We're not creating any electrical current yet. The redox reaction can't happen until we add our last component, which is called the salt bridge. So the salt bridge is called the salt bridge because it's filled with salt. So it's going to have, it doesn't matter what kind it has, as long as it has positive and negative ions that can migrate from the salt bridge into either side. So these ions are going to leave the bridge. It's usually a porous aqueous environment that's either plugged or maybe it's some kind of agar-filled gelatin that allows the salt to move through. These ions are going to move into the half cells in a specific way that I'm going to show you. Okay, so the first thing we need to do is figure out who the anode is. So we go to our table J and we look up our two electrodes. I have a zinc electrode and I have a copper electrode. So zinc is higher up on table J. It's the most active metal. So that is going to be my anode. So we can go ahead and label the zinc side our anode side. And remember, oxidation happens at the anode, anox. So we can write the word oxidation to remind us of that. And the anode is our negative electrode, so we'll label it negative. So on the right, we have our cathode. If zinc's our anode, copper is automatically our cathode, red cat, so that means reduction is going to happen here. And the cathode is our positive electrode. Remember the little T in cathode is kind of like a positive sign, so I will label that electrode positive. Okay, remember our phrase Leo says Gur. So Leo stands for lose electrons oxidation. So what's happening on this electrode is the zinc atoms in this bar are going to lose electrons as they become oxidated. So we can write a half reaction for that in the upper left-hand corner. So this is showing that these zinc atoms that are in this bar are turning into zinc ions by losing 2 electrons. So what happens in this zinc bar is it's disintegrating or falling apart into zinc ions. I'm putting more zinc ions into this half cell aqueous solution here. And the electrons that are lost because of this are going to move up and over the wire into our cathode. So the way you show that in these diagrams, the direction of the electron flow, is by drawing arrows. So this is why it's really important to identify who's the anode and who's the cathode first, because if you have it messed up, the arrows will go the other way and you'll get everything wrong. Okay, so the electrodes have flown from the anode over the wire to the cathode, and they're now in the cathode. So remember, at the cathode, reduction happens. And if we remember our phrase, or our little saying here, Gur, gain electrons reduction. So who's going to gain these negative electrons? Is it going to be the copper 2 ions or the chloride ions? Well, of course, it's going to be the copper 2 ions. So they're going to be 2 positive. They're going to be attracted to these 2 negative electrons. So this is the half reaction for the reduction that happens on the right here. The copper ions that are in solution from this aqueous environment that we added are going to gain 2 electrons to turn into solid copper. And that is going to happen on the surface of the cathode. So this bar is going to get thicker and coated with copper over time. Now I'm not showing it over here, but this bar is actually going to disintegrate and fall apart and get smaller over time. So one reason this reaction will stop the flow of electrons and the electric current being produced over this wire is if this zinc bar disintegrates. If this bar disintegrates and comes out of this aqueous environment, it can't be oxidized anymore. There'll be no more electron flow. Another thing that could stop this reaction is if the electrical potential of these two half cells gets thrown too far out of whack. So on this side, as this bar becomes oxidized and turns into zinc ions, this side is going to become more and more positive over time. Over on this side, as the copper 2 ions get reduced to copper atoms on this bar, I'm going to have a lot of chloride ions left over, and this side is going to become more and more negative. So if this gets thrown off too far, the reaction is going to stop. So as long as we can keep the aqueous environments neutral, this reaction can keep going. And that's the purpose of the salt bridge. So as this side becomes more and more positive, negative ions from in here from the salt bridge are going to flow into this half cell. And on this side, as this side becomes more and more negative, the positive ions are going to flow in and neutralize this solution and keep it at a zero electrical potential for as long as possible. So eventually this salt bridge doesn't have an unlimited supply of ions. Eventually the ions are going to run out, and that could be another reason why the electrochemical cell or the battery stops producing electricity. Okay, so next we're going to watch this little video. It might be a little easier to follow than the animation. This is just a video showing the operation of an electrochemical cell.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution, and the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a voltmeter to the cell shows that electrons flow from zinc to copper. The voltmeter reads 1.103 volts. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
So in summary here, electrochemical cells are spontaneous redox reactions. So they're spontaneous in that we didn't need to do anything other than add all these pieces together in the right arrangement and we start producing an electric current. We don't need to add energy to start the reaction. Their job is to convert chemical energy into electrical energy, meaning like their battery. And you're going to need to know all the parts of an electrochemical cell. You should be able to label one that is not labeled using all of the knowledge like table J and the direction of the electron flow and where oxidation happens, where reduction is happening. You need to be able to determine the anode and cathode. Table J will tell you that the more active metal is the anode and the least active metal is the cathode. You need to know the charges of the electrodes. Remember, the anode is negative. We remember that because the little line in between the A is kind of like a negative sign. And the cathode is positive. The T in cathode is kind of like a positive sign. You need to be able to label the direction of the electron flow. It's always from the anode to the cathode. The more active metal is the anode. Active metals lose electrons. So the electrons are always going to be lost from the anode and travel to the cathode. Those negative electrons will be attracted to the positive side. You also need to know where oxidation and reduction take place. There's a little phrase or trick to help you remember that. Anox, red cat, oxidation at the anode, reduction at the cathode. You also need to know what happens to the electrodes over time. Remember, the anode is losing electrons and turning into ions, so it's going to disintegrate and get smaller. And the cathode is going to gain ions and electrons, and you're going to reduce solid atoms at the cathode, and it's going to get plated or bigger over time. You should also know how the cell stops working. Eventually the anode can disintegrate and no more electrons will be able to flow, or the salt bridge can get depleted and keep the electrical potential of those two cells becoming something greater than zero. So that's it for electrochemical cells. This is obviously a pretty complex process. We're going to need to practice this a lot in class. But if you have any questions, please let me know.